Hey everyone, welcome back to another free prep hour. I'm your host, Tyler Johnson. I am an instructor and tutor here with Manhattan Prep. And these free prep hours are an opportunity for us instructors to take an hour and explore a topic of the GRE. And today, what we're going to do is take a closer look at quantitative comparisons, which are a question type unique to the GRE. You likely haven't seen something like it in the past. It's a pretty specific thing. This session, we'll take a look at what these questions are and how they function, and explore some of the best strategies to apply for these types of questions. And if you're watching this recording, it's been uploaded to YouTube, but this session is also happening live in my Zoom room right now. So if you want to attend one of these sessions live in the future, check the description down below and there should be some links there. To everyone here live in the room, go ahead and open the chat box and tell me where in the world you are connecting from, because I'm in San Francisco, California right now, and it is a lovely sunny day out there, but I'm curious to see where else we have people joining from. All right, we got Orlando, Florida, Minneapolis, Minnesota, Maryland on the East Coast, North Louisiana, Canada. We got an international crew here. Texas, nice. I used to live in San Antonio. Go Spurs. And Peru as well. Thank you all for joining. As mentioned, we're talking about quantitative comparisons. So let me talk a little bit more about the quant section generally. So your first of 12 questions. You'll have 21 minutes to complete it. And the first four that you see on that section are going to be this type that we're talking about today, called quantitative comparisons. After those four questions, you get something that we call discrete quant, or DQ for short. And that's just kind of our terminology for the more regular math questions. That includes multiple choice, select all, and fill in the blank. Questions 6, 7, and 8 on your intro section are going to be data interpretation. That's where you get 3 questions based on a chart or a table. There's some sort of visual component. And then you'll close your introductory section with some more discrete quant. Your second math section looks similar, but it's going to be a little bit longer. Rather than 12 questions, the second one you see is going to be 15 questions, but still you start with quantitative comparisons, though there's going to be 5 on your second section versus 4 on the initial. And in your second section, there is no data interpretation. So after those 5 QC questions are done, it's all discrete quant until you get to the end of the section. So QC, it's always the first 4 or 5 questions you see on your section. And they look something like this. You have a quantity A and a quantity B. Sometimes, but not always, there may be some upfront info at the top of the question. And one thing that is always consistent is these 4 answer choices. On any quantitative comparison, these 4 answers will always be the same, so you should commit them to memory and understand what they mean. And to translate them, answer choice A reflects the situation where quantity A is always the bigger value. Choice B is the opposite, that quantity B is always the bigger value. Choice C is the case where the 2 quantities are always equal, and always being the operative word there. If it's ever a situation where it's not consistent, if it's sometimes they're equal, but sometimes quantity B is greater, anytime there's more than one relationship possible, that would make the answer D. And in terms of answering these, what do I do with my scratch paper? Is I usually write an A and a B, put 2 lines under it for my 2 quantities. I'll retranscribe any upfront info, and then I'm just going to solve from there. So here we know x is equal to 2, so I can substitute that into quantity A. So I see it's 4 versus 5. 5 is always bigger than 4, so that would make the answer B. So that's a more straightforward example, but I'm going to show you another problem here, and I'll give you a few minutes to try it out. If you're here in the Zoom room, chat your answers to me when you are done. Here it is. So to answer something like this, I think it's perfectly natural to perhaps pick some numbers for x and y that satisfy that equation. And a lot of people will jump to something like this, that maybe x is 2 and then y would be 1. And that's a case where quantity A is bigger, but you never want to stop after just one trial. If you are picking numbers on a quantitative comparison, you want to test a few different values to make sure you've examined all the possibilities. And though quantity A will be bigger when I use positive values for the numbers I pick, if I instead did negatives, that yields a case where quantity B is bigger. And at this point, I found two different relationships between my quantities. So that means the answer would have to be D. And this idea right here, as soon as you get two different relationships, the answer is D. We often call that proving D for quantitative comparisons. So in this example, as long as you find two, it could be any two relationships. You don't have to find all three possibilities. As long as you find two, your work is done. You've proven that the answer must be D at that point, and you can move on from the question. So relatedly, we talked about picking numbers just now. A natural follow-up to that is, how do I decide what numbers to pick for these problems? And for that, I've got a mnemonic I want to share with you all. So this is something called ZONEF, where Z, O, and N are going to stand for 0, 1, and negative. E is going to represent extremes, which depending on the confines of the problem, that usually means really small or really big values. So for example, if I had some information that X had to be between 2 and 3, the extreme cases to consider would be a value really close to 2 and a value really close to 3, but still inside that range. And finally, F is going to represent fractions, but not just any fractions. This is less about improper fractions and more specifically about your natural fractions. So negative fractions between -1 and 0, and your positive fractions between 0 and 1. And this isn't necessarily a checklist, right? I don't want you to test like 0, then 1, then negative, then extreme of fractions. Don't feel compelled to do them in order. Instead, what I would recommend when you're picking numbers is always start with an easy case. Pick a 0 or pick a 1. Doing that is going to make the math pretty straightforward. And then you want to get weird with it. So after you start easy, you have a 50-50 at that point, right? It's either going to be consistent and be the relationship that you just found when you picked a 0 or a 1, or you're going to be able to find multiple relationships, and that proves the answer is D. To figure out which case it's going to be, that's where you test the weirder values, like negatives, fractions, extremes, or combinations thereof. And I also want to highlight this list isn't exhaustive. When I'm trying to test some weirder values, it's always going to depend on the context of the problem, right? If the problem itself is using language about divisibility and primes, then I want to make sure I test a number that is prime and is not prime. If it's about odds and evens, I got to make sure I test an odd and test an even. If it's about multiples of 6s, test something that both is and is not a multiple of 6. So as you get further in your studies, you'll kind of see the different language and different concepts that you might be tested on. And that's always going to be, what you're thinking about when you try and get weird with it. What are some maybe edge cases that could break the original relationship that you found when you tested a 0 or a 1? So here's another problem. I want you all to try this one out and see if you can use what we just talked about regarding proving D and using zone F. So if I want to take the ZONEF approach here, I'll start simple, something like a 0 or a 1. Either of those two values is going to create a situation where my two quantities are equal. But we don't stop after just one trial. We want to make sure we also test some weird values here. And if I go with a negative next, like -1, that creates a different relationship where the square is bigger than what I started with. So at that point, I've got my two different relationships, and I've proven that the answer is D. And now an extra credit question on this problem here. What sort of numbers would make it so quantity A is bigger? What kinds of values would create that relationship? Good, if I used a positive fraction. And a lot of people are chatting in fractions generally. I'm gonna push back against that a little bit. I want you to think less just fractions themselves, and more specifically, the differences between negative and positive fractions. Because if I used a negative fraction, the square in quantity B is still gonna become bigger. It's only when I use a positive fraction will quantity A stay the larger value. Okay, let's try another exponent problem. This one's a little trickier. Check it out. In this situation, we have two rules. We know x is an integer and x is smaller than -1. So if I think about zone F, I can't use 0 because we have to be smaller than -1, and I can't use +1. And x is an integer, so I can't use fractions. So my go-tos here should be negatives and extremes. And the largest that x could be, and when I say largest, I'm not talking magnitude, but rather the furthest right x could ever be on the number line would be the case where x is -2. And in that case, quantity A is bigger. And I encourage you, think about the number line whenever you can when it comes to quantitative comparisons, because it's really easy to jumble up magnitude versus being bigger, right? -32, that's bigger magnitude. But whatever value is further right on the number line, that's always what the answer is going to be. So -8 is further right. There's a case where quantity A is bigger. I don't know the answer is A necessarily, though. I want to make sure I test some other possibilities. And rather than jump to something like x equals -3, I would say you want to get a little more extreme with it. Don't just test an integer right next to what you just did. Try and push it a little further out. And there's a certain case I can test here that plays really nicely with exponents. What's a value I could use as a base that's really easy when it comes to exponents? Good. So people are saying in the chat, something like -10. And if you don't know, the trick with powers of 10, the number of zeros is just going to be equal to the exponent. So -10 cubed, it's going to have 3 zeros. And for quantity B, -10 to the 5th power, it's going to have 5 zeros. And again, don't mix up magnitude. Make sure you're thinking about what is further right on the number line, and it's still quantity A. And at this point, I've tested some pretty extreme cases. I think it's a good idea to kind of pause and check in and ask myself, could I pick anything for X that would ever change this relationship? And no, I can't. It's always going to be coming up A, no matter what. And a different way to approach this, what we did here was kind of number picking. But another possibility, something that I'm a fan of, is thinking about the shapes of these functions. So if you were to graph out x cubed versus x to the 5th, it looks something like this. And I know on the real test, you're not going to be able to draw something out like this. You're not going to have graph paper or any visual aids. But I think it's a good idea to at least become mentally familiar enough with the shapes of common functions so you can roughly visualize how they would appear. And what I notice is there's a few different zones here where things are behaving similarly. First of all is when my input is 1, 0, or -1, that's where these two functions cross over one another, and they are exactly equal, right? 1 cubed is equal to 1 to the 5th, 0 cubed is equal to 0 to the 5th, and -1 cubed is equal to -1 to the 5th. And when I have big positive values, right, positive values bigger than 1 in this area, that's kind of the intuitive range. Those are the kinds of numbers we deal most with in our day-to-day lives. And that's a situation where the 5th power is bigger than the cube. But we also get something similar whenever we have negative fractions. And things cross over, right? After we get smaller than 1, we kind of enter this bizarre world where the cube is actually bigger than the 5th. When you cross over 0, it matches the intuitive range. And then when you cross -1, it's kind of bizarre again. So just being familiar with those crossover points and the fact that, for big positives, my 5th power is going to be bigger. But every time I cross over one of those purple points, things are going to flip back around. So if you have a good sense of that in the previous problem, you can just quickly identify for anything less than -1, the cube is always going to be bigger than the 5th. It's further right on the number line in those cases. So that's a cool, interesting visual trick I like to use. If you want to explore that further, there is another prep hour video I've done. I believe the title for that is Functions, like hacking QC functions, something like that. If you look up free prep hour and functions, you should be able to find it. And to kind of extend what we talked about earlier with ZONEF, like yes, ZONEF. That's a great mnemonic for remembering common numbers you want to test. But to extend that a little further, think about the number line here. There's these three crossover points, 0, +1, and -1. And then you've got your big extremes, really, really positive values, really, really negative values. And then you have your two different kinds of fractions, right? Separate that thinking. It's not just fractions as one general blob. Negative fractions often behave differently from positive fractions. So it's these, 4 regions and 3 points, 7 things altogether. That's kind of my full pool of types of numbers I'm looking to draw from when I'm picking values. Okay, we're going to go to a different quantitative comparison strategy next. And before I say more, I just want to toss you all into the deep end and show you a problem here. So try it out, and then we'll talk about the philosophy behind this one. Okay, so first common misconception about this one is I often see people try and grab a calculator. That's not going to work for a problem like this because the maximum display size on the GRE calculator is only 8 figures. So like 99 million, that's the biggest number the GRE calculator can display. And this number here is going to be pretty big. So not only won't it fit there, but more fundamentally, this test is not trying to evaluate whether you can compute giant numbers like the product of all the integers 20 to 30 or a number like 30 to the 11th. So when you see giant numbers, don't compute them. Try to find a pattern or use logic instead. And what's going to help you out here is just to think about what quantity A and quantity B look like if you expanded them out into mathematical notation. So quantity A, I've got these 11 numbers multiplied together. And that number 11 is going to be important. Like you might have seen the 11 powers of 30 there and questioned why 11. Well, it's because we're just comparing 11 different numbers. 30 to the 11th power. It's this long chain of 30s all multiplied together. And what you'll notice is aside from these last two being equal, quantity B is bigger for every other value being multiplied here. So just by using that logic alone, I know quantity B is going to be the bigger value. So a little mantra when it comes to quantitative comparisons is that you need to compare, not calculate. You don't need precision for these kinds of questions. I don't care what the actual number behind quantity A or quantity B looks like. All I need to do is determine which of those two is the bigger one. And I can often do that really roughly using estimation and using logic. So compare, don't try and be precise. You often don't need it. Here's another problem with some similar logic behind it. Try it out. The most common mistake I see for something like this is people will see these variables A, B, C, and D, and then try and pick numbers for quantity A and quantity B. But that's going to create a whole big mess of algebra. There's an easier way to approach things here. And regarding picking numbers, what I'll say, you should always try and simplify first before you pick numbers. Get things down to their simplest form. And ideally, if it comes time to pick numbers, you're only picking in one single place. Right now, I've got 4 variables. I'd be picking all over the problem. The more picking I have to do, the more of a pain it's going to be. So picking numbers right now, it's kind of rough. It's problematic. I want to see if I can simplify things further. And if your number sense is strong, you'll start to see that there's a pretty big connection between these elements of quantity A and quantity B. And if I distribute that AB through the parentheses, then I'll get something that is identical to that first chunk of quantity B. Once you realize that these two pieces are exactly the same, the fact that we're subtracting 2 from quantity B, that's going to cause it to move further left on the number line, and that ultimately leaves quantity A as the bigger value. So don't jump straight to picking numbers. Make sure you simplify as far as you can first. Okay, here's another one. This one's pretty tricky. Give it a shot. Here's another situation where we have a really big product in quantity A, right? We'd be multiplying 24 different fractions together. And this test is not trying to see who can actually do that, right? We're not trying to calculate. We're just trying to come up with a comparison here. And anytime there's like a huge sequence or a long set of consecutive values, I think what's helpful is to just kind of think about the first 3 and the last 3. So for this set Y with all these fractions of the form n over n plus 1, it looks something like this. And just having written it out, some of you might start to see what the pattern is. Because if I were to multiply all these different fractions together, what's going to happen is a lot of those numerators are going to start to cancel with the subsequent or the previous denominators. In fact, the only numerator and denominator that are going to remain after everything else cancels are the 1 and the 25. And that makes these two quantities equal. So don't be tempted by the huge calculations. That's never the goal in these problems. Instead, they're trying to evaluate who can use logic, who can use reasoning, who can find a mathematical pattern to change a huge calculation into something more simple. Okay, I've got one other technique I want to show you. I'm going to begin with a little demonstration here. So say we had a pretty straightforward comparison that 10 is obviously bigger than 6. Notice that if I were to do the same operation to both my quantities, that relationship would be upheld. That if I add 5, quantity A is still bigger. And I could subtract. As long as I subtract the same thing, quantity A is still bigger. I could multiply, quantity A is still bigger. I could divide, quantity A is still bigger. This relationship will always stay the same, except there are some cases where I could actually reverse the relationship. What's an operation I could do here that would cause quantity B to be the larger value? Good. I see some people have it in the chat. If I were to multiply or divide by a negative number, that would switch quantity B into the bigger value. So the logic here, it's kind of like thinking that the person who wrote a quantitative comparison, there's this box between the two quantities, and that box might contain a greater than or a less than or an equals, or I'll call it a question mark for the D situation. The person who wrote the question knows what's inside that box. You, as the test taker, don't, but you're allowed to manipulate the two quantities based upon the same rules that apply for an inequality. That is, you can do the same operation to both sides, except you typically want to avoid multiplying or dividing by a negative number because that would reverse the sign of that inequality. And you don't want to find the reversed version. You want to find what was originally the relationship between your two quantities. So let me show you a more practical example where you could do something like this on the GRE. Say we had a quantitative comparison that looked like this. And some of you might see the square there and be tempted to try and factor this, but that would be overkill for this problem. Instead, you just want to notice what's common between the two quantities. The fact that we have a 12a squared in both, rather than factor that, what I could do to make the math easier is just subtract that exact value from both quantities. And now the scariest part of the problem has disappeared. I just subtracted it out. And I can keep going from there. Ultimately, the goal is I want to isolate my variables under a single quantity. So that way, if I need to pick numbers, it's happening in as few places as possible. If I tried to pick numbers in the base version of this problem, there's 4 different spots for A. I'd have to do it. 2 of those would be getting squared. It's a mess. But after I manipulate the two quantities, thinking of it as like a hidden inequality, now I only have to pick numbers in one spot. So my life is a lot easier. And the only restriction in this problem is that A is positive. It's bigger than 0. And it's not too difficult to test a few cases where you produce different relationships. So this is another problem where the answer is D. So to recap that, the rules here, you can add or subtract anything. Addition, subtraction, that's always safe. As long as you add or subtract the same thing from two quantities, you have not impacted whatever the relationship is. Where you have to be careful is whenever you multiply or divide, ensure that it's only by positives. And be careful too, if it's a variable and you're not sure whether it's positive or not, that is not a safe move. It's only when something is guaranteed to be positive that it is safe to multiply or divide by. And then big picture, I think what your goal is, you're trying to isolate the variables underneath one single quantity, push them all together in one single spot. So when you pick numbers, it's only happening in one place. I'm going to show you another problem where this logic can be applied. Try this one out on your own. One tip I have off the bat here is to rewrite the upfront info so it references an expression in the quantities. Because right now, y does not appear alone in the quantities. It's always grouped with that +1. But if I take that initial inequality and just add 1 to each side, now I get this information that y + 1 is known to be positive. First thing I would do to simplify across the two quantities, though, is notice that z that's kind of slapped onto both quantities. That's just hanging out there on its own, so subtract that out. And then from here, recall that we have discovered that y + 1 is something positive. That makes it safe to multiply or divide by. Now, if you did this without acknowledging that y + 1 is positive, be careful. That can cause some trouble later on. You never want to you never want to multiply or divide unless it's by something you've proven to be positive. So compared to where we started, things are much simpler. Now we've just got X for quantity A and 2X for quantity B. And I don't have any restrictions on X. So I can just pick a few different values. And now I've proven that two different relationships are possible. So the answer is D. Here's one other problem where I think using that hidden inequality to simplify across is the best move to make. Try it out. In the upfront info, we know that Y is bigger than Z, but a more helpful way of expressing that for this problem is going to be subtract a Z from both sides. And now you see this expression Y minus Z, that is something we know to be positive. So I can divide it out from both quantities. Make sure you aren't doing that until you know it's positive. But after doing so, we're left with X plus Y versus X minus Y. So go ahead and subtract those X's out. And then it's just Y versus negative Y. And guess what? We know Y is positive. That means quantity A is always bigger than quantity B. Okay, I got one more problem to show you all, and then we're going to start wrapping up. So last problem of the day, check this one out. In these two quantities, we have these really large chained sums. But by now, you've heard me say this a few times, we're not trying to actually calculate those sums. We're just trying to get a comparison between these two quantities. So when you've got long operations, whether it's a huge product, huge sum, best thing to do is just write out the first few and the last few terms. And what you'll notice is there's a lot of overlap between these two quantities. So I can effectively just subtract all of that overlap from both of my quantities. And really, I'm just focusing on what's different. And what's different actually turns out to be the same. Both these sums are now 90. So the answer is C. Okay, so to recap a lot of what we talked about today, I think the most important bits here are picking numbers is a great strategy for quantitative comparisons. And some of the most helpful ways to guide that is to think about zone F and think about those regions on the number line, right? Your big positives, your big negatives. A kind of quick reference to that I often draw out is something like this, where I've got my big negatives and then -1, and then my small fractional negatives and then 0, and then +1. Actually, between 0 and +1, you have your positive fractions, and then you've got your big positives beyond 1. All right, so those are like the 7 different areas that are great to pull from when you are picking numbers. Likewise, proving D, that's kind of the best approach here. As soon as you find 2 different relationships, you can stop. Your work is done. You have proven the answer is D at that point. So pick easy to start, like a 0 or a 1. From that point, you're trying to pick something that'll break that original relationship. If you can, you've proven it's D. If the same relationship keeps consistently appearing, then it's probably A, B, or C. And remember, you don't need to know what the exact values are behind these quantities. Your only goal with these sorts of problems is to determine which quantity is bigger. So rather than calculate, rather than be precise, just try and make that comparison. And you can often do that with estimation and using some rough logic. Also, don't forget about the hidden inequality. That's one of my favorite techniques for quantitative comparisons. As long as you do the same operation to each side, you can add or subtract anything you want. You can also multiply and divide, but you have to make sure that is only by positives. If you were to multiply by a negative or a 0, it jumbles up the original relationship, and that's not what you're after. And the goal there, try and isolate the variable under one quantity. So then if you do end up picking numbers, you only have to do it in one spot. And then overall, the kind of zoomed out big idea process here is for any quantitative comparison, start by simplifying first. That can be a matter of simplifying the upfront information, right? Like rewriting one of those inequalities to actually reference something in the quantities. It can be simplifying an individual quantity, or it can be applying the hidden inequality to do both at the same time, where you're moving pieces across the two quantities. After you've simplified as far as you can go, that's when you can pick numbers, but don't start there. You have to simplify first and then pick numbers later. All right, so that does it for today's free prep hour. If you enjoyed this, I encourage you to check out a live one at some point in the future. I will provide a link in the chat if that's something y'all want to check out if you're here in the Zoom room. If you're watching this on YouTube, there should be a link down in the description. And in addition to our free prep hours, we also open up session 1 of our 9-class course up to the public. So if you want to check out a full 3 hours with one of our instructors, you can find those at that same link on screen and in the description. So I'm going to go ahead and stop the recording. If you're in the room right now and you have any questions for me, you're welcome to ask those afterwards. But yeah, it was a pleasure having you all here today. Hope you had some fun. I'll see you next time.